Hi viewers, welcome to my class on heat transfer. In this class, I will give a brief introduction to the boundary conditions used in various situations while solving problems. Solving the heat transfer problems, we need to define certain boundary conditions. Different situations will have different boundary conditions used. Generally, there are three boundary conditions. One is boundary conditions of first kind. It is prescribed temperature boundary conditions. So for a surface, if the temperature is specified, so at this point the temperature is T1 and the other end temperature is say TL at a distance L from this point. If you take this as y-axis, at x is equal to 0, we have temperature T1 and at x is equal to L, temperature is TL. So we are specifying the temperatures. Somehow we are maintaining the temperature is constant. Here also temperature remains constant. So if you can specify the temperature at a given point, that is the constant temperature boundary condition. And here the condition is at x is 0. So taking this as y-axis, at x is 0, that is first one is spatial coordinate, that is x is 0. This is taking as a one-dimensional heat transfer. One dimension means heat is flowing only in one direction, not in y direction or z direction. So only in one direction is heat is flowing. So I have taken only one spatial parameter. So temperature can be defined with the x, y, z and with respect to time also. So here I have taken only one spatial coordinate, only x direction. So temperature at x is equal to 0 and time t, the given time is t1. So we are specifying the temperature at a given point, that is x is equal to 0 as T1. Again, temperature at x is equal to L is at a given time is T2. So specifying the temperature at any surface like this, constant temperature you are specifying like this, that is temperature boundary condition. So temperature is specified at the boundary of the surface and it is temperature boundary condition. Now if you are specifying the heat flux instead of temperature, we have like so much heat is flowing into the surface and so much heat is flowing at the other end of the surface. So any surface, you need not have both. Here you may have temperature boundary condition, here you may have heat flux boundary condition. So if you are specifying that so much of 10 watts of heat is flowing into the surface when x is equal to 0, that is a heat flux boundary condition or boundary condition of second kind. So if the rate of heat supplied to a boundary is constant, such a heating and the boundary by electrical heater or boundary condition is called heat flux boundary condition. So to maintain this heat flux, you may have an electric heater attached to this, which might be supplying the heat at a constant rate. So we are not worried about that. We are just specifying that so much of heat is supplied at the surface. So much of is the heat flux at this point. Q0 is the heat flux when x is equal to 0 and QL is the heat flux at x is equal to L. Specifying that is called heat flux boundary condition. So when x is equal to 0, that is this point at this surface, x is 0, Qx is equal to x is 0. So Q0 is equal to minus k dt by dx at x is equal to 0. So the heat flux, we have specified the heat flux as Q0 is equal to minus k dt by dx at x is equal to 0. So that is heat conducted from this. Heat flux is so much, it will be conducted from that point. This is by Fourier law of heat conduction. Per unit area, A is not there. So per unit area, so much heat is conducted away. So heat flux, whatever heat flux is taking place, so much heat will be conducted from that point. Otherwise, temperature will not be steady. The heat flux also will change. So in a steady state heat transfer process, heat flux at the surface is equal to heat conducted at that surface. So Q0 is equal to minus k dt by dx at x is equal to 0. Similarly, at x is equal to L, the heat flux is QL. QL is equal to minus k dt by dx at x is equal to L. The heat flux at the surface, it may be like a positive or negative, it can be flowing out also. So QL is equal to minus k dt by dx. Whatever heat is conducted is equal to QL. QL can be either towards the surface or from the surface. So based on that, it can be positive or negative. So whatever heat is conducted is equal to heat flux at that surface. So heat flux is equated to heat conducted. This is heat flux boundary condition. Next is convective boundary condition. Convective boundary condition, convection is specified. Convection at a surface is specified. Convection heat transfer coefficient is specified. So H is the heat transfer coefficient at convection, and the convective heat transfer, when the convection heat transfer coefficient is given, convective heat transfer is H into temperature difference per unit area. For unit area, H into temperature, HA delta T as per Newton's law of cooling. Convection heat transfer is HA delta T. So H into temperature difference, H into T1 minus T infinity. Here the temperature difference is T infinity minus T1. Heat is flowing from the fluid to the surface. So I have written H into T infinity minus T1 at x is equal to 0 is equal to heat conducted out from that. For steady state process, heat convected is equal to heat conducted. For steady state process, heat convected is equal to heat conducted out. So H into T infinity minus T1 at x is equal to 0 is equal to minus k dt by dx at x is equal to 0. In the similar equation, you can write on the other end H into T2 minus T infinity. T infinity is the temperature of the fluid here, and T2 minus T infinity is the temperature difference. H into T2 minus T infinity is equal to heat conducted is minus k dt by dx at x is equal to L. This is a boundary condition of third kind, a convective boundary condition. So these are the three boundary conditions usually used in heat transfer problems. Thank you for watching.